So I wanted to take a moment and review the definition of the definite integral that we just talked about with the paper example. And so the definite integral from a to b of f of x dx we defined back in Calc 1 as the limit as n tends to infinity of the sum I equals 1 to n of f of xi star, and we'll say delta x. I'll just say delta x actually. So the idea was something like this. If you have a curve, let's say here's our f, and here's A, and here's B. We broke up the interval into n pieces, each of width delta x, and we picked a test point in each little piece. Let's pick this as our test point. We go up to F, and then we build a rectangle over that piece, and the height of the rectangle would be f of xi star. And here, I is going from first piece, I is 1, I is 2, I is 3, so on and so forth. And so the idea was the area of this rectangle is f of xi star times delta x, and the sum of these is going to give you an area that's pretty close to the area that you want, the exact area under the curve. And so the idea is you can get the precise area by computing more and more and more rectangles. So the finer you go, the more rectangles you put in here, the closer you get. And if you take the limit as the number of rectangles shoots towards infinity, that's going to give you the precise area. Well, let's keep that in our minds as we go along here. So what we want to do for our setup is I want to start with a two-dimensional curve that's parametrized. So I'm going to assume that I'm parametrized by r of t for t between a and b. I do want to assume that c is traversed. You go around c exactly once as t goes from a to b. So for example, I don't want to go around c and then go around c a second time. I want to just go around c one time as t goes from a to b, assuming it's closed. Even if it's not closed, I want to start here and go there. I don't want to do this kind of thing. Does that make sense? Want to avoid that if possible. Okay, so we've got that set up, and then I want to have a continuous function f of x, y, z. So pause for a moment. You should be able to recognize both pieces. We'll do the space curve in red. So I've got some space curve that's looking like this maybe down here in the xy plane. I'll do my surface in green. So I've got some surface living above this curve. Maybe it looks like that. All right, and so just like what we talked about in the first video with the paper example, I can actually, I'll use, I don't know, let's find something nice. Let's use purple. I can extend up, and I get I get a wall. I can extend from my curve C up to my function, and I get a wall, and it looks something, wow, that was terrible. Let's try that again. It's going to look something like that, and yeah, you can use your imagination. But you get this curvy wall, just like what we did in the video example. And so the question is, can we find a way to form an integral of f along this c in a meaningful way? And so the idea is, I'm going to do some squeezing here. First off, let's move that over there. Second off, let's make a couple of points. So you actually want to break up the interval from a to b into n pieces. You don't want to try to break up your curve into n equal pieces. Break up the interval AB into n equal pieces. You can do that. AB is just this line segment, and so it's easy to divide it into n equal pieces. When you do that, you actually will also break up your curve into n pieces. They might not be equal length, but there's going to be n pieces. And then you're going to pick a test point on the curve for each piece. So you can pick a test point there, test point here, test point there, test point there, so on and so forth. And you can actually form areas. So you get a little piece of area. It's kind of bent a little bit, but I get this area, and I go up, and the height is going to look like that. You plug this point into your surface. So the height of the area is going to be f of xi star, yi star, and then the length here is going to be the arc length. That's the key, is you have a little piece of arc length. And so that brings us to the definition of the line integral. And so this is the line integral of f along C with respect to, I abbreviate with respect to WRT, with respect to arc length. And it's really important that you keep track of what kind of line integral we're doing with respect to what, because we're going to have line integrals with respect to different things. So this is defined as the limit as n goes to infinity, sum I equals, should not be infinity, I equals 1 to n of f of xi star yi star times the little piece of arc length. And the arc length will change here actually. So it is, the arc length depends on your actual piece of the curve that you're looking at. Now this line integral is defined whenever this limit exists. That's all fine and good. I wanted you just to see the similar definition here that you saw back in Calculus 1. I'm not going to ask you to compute anything with this definition. We're really faced with the question right away, how do we actually evaluate line integrals practically? It's not practical. As fun as those limits might be, it's not practical to work that out. So let's do that. Real quick though, before we look at that, I just thought of one more thing. I just want to highlight the ds right here at the end. The ds indicates with respect to arc length. And we'll talk more about that in just a minute. So you're going to see me write ds's a bunch here. All right, so back to our question. How do we evaluate line integrals practically speaking? Well, I want us to look at the line integral over C of just the function 1 ds. And keep in mind, f of xy equals 1 is just this flat plane. It's just a flat plane of height 1 sitting over the xy plane. Kind of boring, but it's going to be just what we need to see what's happening. I don't like the color purple anymore. Let's go back to black. Okay, so then, well, by definition, by our interesting definition above, this integral is the limit as n tends to infinity of all the little pieces of arc length. Whoops. I need to, the sum of the little pieces of arc length, so I equals 1 to n of the SI. But if you think about it, each time when I add these up, I get the whole arc length. So right away, it's easy to see. You just get the arc length of your curve C. But we have an expression for that. We know how to integrate that. The arc length can be captured as the integral from a to b of the square root of x prime of t squared plus y prime of t squared dt, or if you want, you can abbreviate that as the integral from a to b of the length of r prime of t dt, either way. So, okay, that's all fine and good. That's just this first example. But similarly, one can show that this integral that we're interested in, the integral of any function f of xy that's continuous on our curve, this integral can be captured as the integral from a to b. You plug in your parameterization, so it's f of x of t, y of t. You multiply by this ds you can think of as the length of r prime dt. So you multiply by x prime of t squared plus y prime of t squared dt. And of course, we should all realize that we can shorthand this quite a bit and just say integral from a to b, f of plug r of t into f, multiply by the length of r prime of t dt. So that's how you can work with line integrals with respect to arc length. One quick comment. You might be wondering, does the value of the line integral depend on the choice of parameterization? And the answer is no, it does not. You can parameterize the curve differently and it won't change the value of the line integral. So let's stop this video series here, and then I think we should do an example and see how you actually compute